How do you make the molecular orbital diagram for a B2- ion? Start by writing out the electron configuration for a boron atom. By looking at the periodic table, we can see that the electron configuration for boron is equal to 1s2, 2s2, 2p1. For our molecular orbital diagram, we're only concerned with the highest energy level in our electron configuration, because this possesses the valence electrons, and the valence electrons are involved in bonding, which is what the molecular orbital diagram really looks at. So we're only concerned with the n equals 2 part of our electron configuration. So this is the 2s and the 2p orbitals. So we can kind of just ignore our 1s2 portion here, so we'll erase that. And then we just want to count up the electrons within our n equals 2 energy level. So we can circle our 2 and our 1, which means that we have 3 electrons that will be involved in the bonding, 3 valence electrons involved with bonding in each individual boron atom. So we can write that we have 3 electrons to place into our atomic orbitals. This will go into there. And now we can go ahead and do that. We can place these 3 electrons into our atomic orbitals. So we know that we'll start with our lowest energy atomic orbitals according to the off-bat principle. So these will be the 2s atomic orbitals. So we'll place 2 there, and then 2 on this side. Looks exactly the same. And then we'll go up to our 2p orbitals, where we'll have 1 leftover electron. And this looks good. However, we need to notice that we have a minus sign in our B2- ion. So we have to add 1 more electron to either one of these boron atoms. It doesn't matter which one, but for just this video, we'll take the boron atom on the right, and we'll add 1 more electron to it, because one of these has to become an anion, so that our resultant molecule, the B2-, will have a minus charge. So we'll make this 4 electrons, and then we'll add 1 more electron into our 2p orbitals on this side. And so now our atomic orbitals are filled in. And now we can go ahead and start adding in electrons into our molecular orbitals. So again, we'll start with our lowest energy, according to the off-bat principle once again. And we'll see that in total we need 7 electrons if we add up our contributions from our atomic orbitals. And so we'll start filling up the bottom. The sigma 2s bonding molecular orbital can hold 2 electrons, and these electrons from the atomic orbitals will fall into it. And then the next 2 electrons will rise up to the sigma 2s star anti-bonding molecular orbital that is higher in energy, and will completely fill that up. And then we go into our p orbitals. We have 3 electrons within our 2p atomic orbitals that we can use. And again, we'll start with the lowest energy, the pi 2p molecular orbitals. We have 2 of them, and we have 3 electrons to include here. So we'll fill each one up with 1 electron, and then we have 1 left over to place right there. And there's your completed molecular orbital diagram for B2-. Note here that we have 7 electrons in total filling up these molecular orbitals, which aligns correctly with our number at the top, which is always set forth in the beginning. The total number of electrons always has to be conserved. Okay, so now that we have our molecular orbital diagram, we can start looking at some other things in association with the B2- molecule, and one of which is the bond order, sometimes abbreviated as BO. And the bond order is pretty much a measure of the stability of a bond, or its strength, and it's equal to 1/2 times the number of bonding electrons, which are present in the bonding molecular orbitals, minus the number of anti-bonding electrons, which are present in the anti-bonding molecular orbitals. So, how many bonding electrons do we have? We have a couple bonding molecular orbitals, one of which is here the sigma 2s bonding molecular orbitals. Basically, anything that doesn't have a star is a bonding molecular orbital, and these are also bonding molecular orbitals. So in total, if we count out the electrons within those, we have 5. So we can do 5, and then minus the anti-bonding electrons. This is the only anti-bonding molecular orbital filled up with electrons, and there's 2 of them. And then if we do 1/2 times 5 minus 2, that's going to be equal to 3/2, or we can also say it's equal to 1.5. And that's your bond order for this molecule. A bond order of 1 typically corresponds to a single bond, while a bond order of 2 usually means a double bond. So a bond order of 1.5 is pretty much telling us that the bond in B2 minus is somewhere in between the strength of a single and a double bond. So finally, is the B2 minus molecule paramagnetic or is it diamagnetic? Because B2 minus has an unpaired electron present in this pi2p molecular orbital, this tells us that B2 minus is paramagnetic. And paramagnetism pretty much means that B2 minus will be weakly attracted to an external magnetic field.